In section 4.1, we will discuss inverse functions, and in particular, we will apply these to exponential and logarithmic functions. So, in order to recognize if we have an inverse, we first must determine if we have a one-to-one function. So the definition for that is that each x value corresponds to only one y value, and each y value would correspond to only one x value. Remember, in order to determine if we have a function, we check to see if each x goes to only one y. If it's one-to-one, your y's cannot repeat either. So, one way we could check that, particularly if we're looking at a graph, is we know we have a vertical line test in order to see if something is a function, but we can also use a horizontal line test to check to see if a function is one-to-one. So a function is one-to-one if every horizontal line intersects the graphs of the function at most once. So here are a couple of quick examples for us to observe. Now, on the graph to the left, on A, if we very quickly check our vertical line test, we would see that yes, it is a function. And what I want you to pay close attention to is this area right in here. I know it looks as if there may be a horizontal section there, but hopefully you are recognizing this is the graph of the parent function that is cubic. This is actually going to be the graph of y equals negative x cubed, because everything gets reflected over the x-axis compared to the original. Remember, the original would pass through both the first and the third quadrants. This one is in the second and the fourth. And if we were to zoom in on this area, we would see, although it is close to appearing horizontal, there is never any place that for any x value we put in that we're going to get y values that repeat. So this actually is one-to-one, because each x is going to give us back exactly one y. There are no y's that will repeat either. Passes a horizontal line test, so it's a function. Now it's pretty obvious on B. First of all, I know it's a function because it's quadratic. It's a parabola that opens down. But when I try the vertical line test, there are a number of places, in fact, just about everywhere on this graph, that this horizontal line would cross in more than one place. That means it is not one-to-one. And let's go look at the next. In general, a function that is either increasing or decreasing on its entire domain, something such as f of x equals negative x, or g of x equals x cubed, or h of x equals the square root of x, then those must be one-to-one. As long as it is increasing or decreasing everywhere, it should be one-to-one as long as it is something that is a function. Now, we have a definition here for identifying inverse functions if possibly instead of graphs, we are given equations. And what would be true is that if I were to take the composition of the original function and its inverse, they're identifying the inverse function here to be function g, then f of g of x would simplify to just become x, and g of f of x would simplify just to become x. So that would be a test that I could use to determine if two functions are inverses of each other. Okay, now notice in bold here it says the condition that f is 1-to-1 in the definition of inverse function is essential. Otherwise, G will not define a function. I could get an inverse, but it wouldn't be a function if the original was not a 1-to-1 function. So let's look at a quick test here to determine if these could be inverse functions of each other. So the first thing I'll want to check is to see what happens if I do f of g of x. That means I'm going to take the g of x function and I'm going to sub it into the x value in the f function. So I will get f of my g of x is 1/2 x minus 5. So that's going to go in place of x in the f function. So that would be 2 times 1/2 x minus 5. And then I have a plus 5 at the end. Now, I need to simplify that. If I clean that up, then what I have, I could think of this as 2 over 1. Use the distributive property. 2 over 1 times 1/2 x would just be x, because I would have 2 over 2x. And then when I multiply 2 times -5, I would have a minus 10, and then I would have a plus 5 at the end. Now if I clean that up, I do have like terms here that can be combined. That's going to equal x minus 5. If you recall from the definition, if these are inverses, this has to clean up to be just x. I have x minus 5. That minus 5 on the end. Right there I can stop and say this is not an inverse. These two functions are not inverses of each other, because when I did the composition, I did not get back the value of x. If that happens going one direction, there isn't even a reason why you would need to check it plugging in the other way. It's not going to, it doesn't matter if it works, it's got to work both ways. Now, if this had a plus 10 at the end instead of a plus 5, when I cleaned this up, it would have equaled just x, and then I would have had to test the other way. As long as both of them will simplify to give me x, then it's an inverse. On this third page, we're going to fill in these blanks by the definition of inverse function. What that means is the domain of f becomes the range of the inverse, and the range of f will become the domain of the inverse. Remember, if we are switching x and y values in an inverse, which is actually what we are doing here, then it's pretty obvious that the domain will become the range and vice versa. Now, that gives us the ability to find inverses of ordered pairs very quickly and easily. So, first of all, the instructions tell me to find the inverse of each function that is 1-to-1. So that's the first thing I have to check. Is this a 1-to-1 function? So if I look at all the x values, -2, -1, 0, 1, and 2, they're all different. So I'm good as far as it being a function. For it to be 1-to-1, the y's can't repeat. So -8, -1, 0, 1, and 8. That must mean that it is 1-to-1. So in order to write the inverse, and I will use the little prime symbol, it looks like an apostrophe, after f, all I have to do is switch the x and y values in each ordered pair. So I'm going to have -8, -2 in the first ordered pair. The second ordered pair becomes -1, -1. Now, that's just coincidence. The x and y values were the same on these three ordered pairs in the middle. As you can tell from the first one and the last one, typically when I switch, they're not going to look the same. We just happen to have the same values in those three ordered pairs in the middle of this set. And my last ordered pair would be 8, 2. Be sure you use your braces to close off your set. Now, if I look at set G, again, I've got to double check to see, is this a one-to-one function? So when I check x values, I have -2, -1, 0, 1, and 2. So I'm good with that. But when I check y values, look what happens. I have a 5 here, but this ordered pair also has a y value of 5. I have a 2 in this ordered pair, and I have a 2 in this ordered pair. That means this thing is not one-to-one, and if it's not one-to-one, there will be no inverse. Has to be a one-to-one function in order to have an inverse. Now, it says that the inverse of a one-to-one function is found by interchanging the x and y values in ordered pairs. We just practiced that. If I wanted to find the inverse of an equation, I do it the same way. I will simply switch the x and the y values, and then I will have to solve for y. So let's look at this. If I see that it's in function notation, I can replace that with a y, and this would be y equals 4x minus 7. So in order to get the inverse, I'm going to switch the x and the y, and that would give me x equals 4y minus 7. But in order to write it correctly, I need to have it back in function notation. I need to get the y isolated. So let's add 7 to each side, and that would give me x plus 7 is equal to 4y. And to finish this thing off, there's a variety of ways I can do it. I can either multiply everything by 1/4, or I can divide both sides by 4. That's probably our faster way to do this. And we would get y equals x over 4 plus 7 over 4 if we want to separate it into two fractions. If we wanted to leave it put together as x plus 7 over 4, that's how it would appear as a single fraction. When you do this in homework, if you have a question that asks you to do this, just pay attention to the instructions on how you are to write your answer. Now, page. We're going to determine whether we have inverses from looking at a graph. And it's very simple to determine if we have inverses. There is a dashed line that is showing here y equals x. That would have to be a line of symmetry if we have two inverse functions graphed on the same xy plane. Now, what that would mean is if I were to fold on that line, the two halves have to match exactly. And it means if there is a point of intersection, as there is here, it has to be on the line y equals x. If it occurs any other place, there's no way when this thing folds that I could get the halves to match up. So a point of intersection must be on the line y equals x. If it's any other place, it automatically tells you that these are not inverses. So that's a quick way to check visually. Now, if we come down to this table, we do have some things we should be able to summarize that we've learned about inverses. First of all, if our function f is one-to-one, then that means that the inverse function exists. 2, the domain of f is the range of the inverse, and the range of f is the domain of the inverse. So we know that the x's and y's switch, which naturally means our domains and ranges will switch. Now, if the point AB is on the graph of the original function f, then that means the ordered pair BA would lie on the inverse. And the graphs of f and f prime, the inverse of f, are reflections of each other across the line y equals x. Very important to remember that. And If I want to find the equation for the inverse function, remember first we've got to check to be sure that the original function is 1-to-1. If it is, then we can take our original function f of x, replace it with y, and then we interchange the x and y in the equation and solve for y, and that will give us the inverse function. Next page. Now, what I have are some graphs that will help us to recognize how knowing what inverse functions are can help us as we look for ways to graph functions. Now, remember we said that if we switch x and y and then resolve for y, that's how we would find the inverse equation. Now, the problem is that in the case of exponents, if I had f of x equals b to the x power, in other words, y equals b to the x power, and I'm going to write this over here so you can see it, and I were to switch the x and the y, then the inverse would become x equals b to the y power. And I have a little problem with that, because if my y is now the exponent, I'm not sure how to get it down out of being the exponent and write it as y equals something, unless I understand that exponential functions and logarithmic functions are inverses of each other. All that a logarithm, is a way to solve for an exponent. In other words, I'm asking myself, what exponent would I have to raise the base to in order to equal some value? So when I look at this right here, the inverse function of x is simply saying I'm looking for the exponent that b would have to be raised to in order to get x. That's all that it means. Now, in order to help us out, if I were to look for the inverse of f of x equals 2 to the x, one way I could do it is I could actually plug in to a table, get the graph of that exponential function, and then I'm going to switch the x and the y values. So let's do that real quickly. I just want you to see how this works. Now, you do need to know your exponent rules. So at this point, I'm going to make a suggestion. If you do not remember what negative exponents mean, if you do not remember anything about fractional exponents, there are some review videos that are loaded into the homework section in in my math lab. And if you look, you'll see a review for exponent rules, and you will see some other things that might be helpful for you to go back and look at if you're a little fuzzy on this. I'm going to assume that you remember what all these exponents would be. So if I'm plugging this in where my exponent is a -2, what I do know about negative exponents, they tell me nothing about the sign of the answer. Instead, they tell me about location. It means if I think of this as a fraction, 2 to the -2 power over 1, then I am going to take whatever has that negative exponent and it goes to the other location. In this case, it's going to go down to the denominator, and then I can write it with a positive exponent. So 2 to the -2 power is the same thing as 1 over 2 to the +2 power, and if I were to clean that up, that would give me the fraction 1/4. Now we're going to practice another one of those. Okay, but before we do, I'm going to put this point on my graph. So what I do know is when x is -2, my y value is a positive 1/4. So just, a little above there, I would have my point. Now, if I were to plug in 2 to the -1 power, that would mean that I would have 1 over 2 to the +1, which is just the fraction 1/2. So when x is -1, y is 1/2. I apologize for where my points are. I'm having a little trouble with my stylus. Okay, this is important. What is anything raised to the 0 power? I hope you haven't forgotten that. Anything, any base raised to the 0 power is equal to 1. And that means the point 0, 1 is on this graph. These will be easier. 2 to the first power is just 2. So when x is 1, y is 2. 2 to the second power is 4. So when x is 2, y is 4. And 2 to the third power means 2 times 2 times 2. That's 8. So when x is 3, y is 8. Now, here would be the graph of y equals 2 to the x power. And what we have is an asymptote that is approaching the x-axis. As we get closer and closer to that x-axis, we are never going to actually get to 0. Think about this for a minute. As I take 2 and I put an exponent on it in the denominator, that gives me fractions. And those fractions are going to get tiny, 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 tiny. But if I have 1 divided by something, will I ever have 0? The answer is no, I won't. And I don't have the ability to get any negative values. So that's why I know this is an asymptote. Now recall that we're going to need this dashed line for y equals x, because that has to be a line of symmetry, and we're going to reflect these values in just a minute. Before we do, let's look at this graph and you tell me what you recognize the domain will need to be. Now, domain would be the x values. This thing continues on to the left forever, and even though it's going up rapidly, it is still moving to the right. My domain is negative infinity to positive infinity. If I look at that equation, I don't have any restrictions on what I can use as an exponent. I can put anything in for an exponent that I want. But notice my range. The smallest value I get back is still bigger than 0. So I'm going to have all the positive numbers, but I won't have any negatives and I won't have 0. That means my range goes from 0 to positive infinity, but 0 is not included, so I have to use a parentheses. Now, in order to plot the graph, for the inverse, which would be y equals log b, log base b of x, in this case, this would be the equation y is equal to log base 2 of some value x. What we're going to do would be choose some values of x, but remember our x and y values switch for each ordered pair. So if I had an x value of -2 and a y value of 1/4, in the first ordered pair, x is now 1/4, y is now -2, and if I come over here to the graph, when x is a positive 1/4, y is going to be a -2. So somewhere, well, that's a little off, but you'll hopefully get the idea in a minute. If I switch the next one, when x is 1/2, y would be -1. So when x is 1/2, y is going to be -1. Really having trouble with these fractions with this stylus. Now, if I switch the next pair, when x is 1, y is 0. So right here is the point 1, 0. When x is 2, y will be 1. So that's going to come up here. When x is 4, y will be 2. So if I come out here to x is 4, y is going to be 2. And if x is 8, y would be 3. So here would be 8, there is 3. Now, if I sketch this, here's what we're going to see. This thing is going to curve that direction, and now this thing's going to squeeze closer and closer to the y-axis, but never actually touch. Notice if I fold on that line of symmetry, these halves would be mirror images of each other. They would match up. So that's one reason why it's important to know that exponentials and logarithms are inverses of each other, because it's a lot easier to plug into the exponential, and then I can just switch those ordered pairs. Now tell me what you know about domain. Remember we said if there's an inverse, the domain and the range switch. So since the range was 0 to infinity on the original function, that means the domain will be from 0 to infinity on the inverse, and the range will be from negative infinity to positive infinity. Now, if you look at the next equation, it's really very similar. The only thing that's different is they're asking you to plot the points and graph the function for the logarithmic equation. Well, I can't really do that unless I write this in inverse form, and then I would get it in exponential form. And once I plugged those values in, then I would have to switch them. Let me show you what I mean real quickly. Because if I think of this as y is equal to log base 3 of x, remember this is saying we're looking for the exponent that 3 would need to be raised to in order to get x. So when I switch the x and the y, that means this is going to end up being 3 to the x power. Okay? And then I could take this just as we did above. We would find some ordered pairs to graph, and then we just have to switch them to fill this in. To save a little time, we're going to skip over that. We're going to go to the next page. And let's see what happens if we are working with a fractional base. So this one is already set up to where we have f of x is equal to 1/2 raised to the x power. We know we can plug in there. The inverse, if I were to switch the x and the y, I know means it has to turn into a logarithm, because that means I'm looking for the exponent that 1/2 would have to be raised to in order to give me x. So let's start on the left side. We're going to have to pick some values for x. They didn't give them to us here. So let's use the ones that we did a moment ago. These are kind of your go-to numbers. Try -2, -1, 0, 1, and 2. If we get that, we should have enough to work with to see how to get the graph. So if I were to take 1/2 and raise it to the -2 power, all right, remember what we said about negative exponents. That means that we change location. In other words, numerators and denominators flip. So if I have 1/2 raised to the -2 power, in order to turn that negative exponent into something that's positive, the numerator goes down to the denominator, or the bottom, and the bottom goes to the top. This is going to end up being 2 to the 2nd power, which is the positive number 4. So when x happens to be -2, y is going to be a positive 4. And we're going to put a point there. Now, if I take 1/2 and I raise it to the -1 power, again, the negative exponent tells me to flip that base, and that's going to give me 2 to the positive 1 power, which is just 2. So when x is -1, y is positive 2. All right, what did we say? Anything to the 0 power equals 1. And you should tuck into your brain, if I have any exponential equation, it doesn't matter what my base is, whether it's a fraction, whether it's a whole number, and by the way, we're only going to be looking at positives, so we're not going to see any negative bases, and you won't ever have 0 as a base. But that tells me that I'm always going to have to pass through the point 0, 1 when I graph this. If I take the fraction 1/2 and raise it to the 1st power, that's just the fraction 1/2. So when x is 1, my y value is 1/2. And if I were to take 1/2 and square it, I get 1/4. So when x is 2, my y value will be 1/4. And notice what happens here. I still have the same shape on my curve, but it's going the opposite direction. If you look back at the other function, that exponential that had a base of 2 was increasing everywhere on the domain. And that will be true for any exponential function where the base is greater than 1. but this one had a base of 1/2. So if your base is between 0 and 1, then your function will be decreasing over the entire domain. Now, let's go ahead and write out what the domain and the range would be. Do I have any restrictions on x values? Can I have any value I want as an exponent? The answer is yes. If I check this graph, it's going to keep going to the left and keep going to the right. So negative infinity to positive infinity is my domain. My range is still restricted to positive values. So I'm going to have from 0, not included, up to positive infinity for my range. Now, in order to graph this inverse, I'm going to sketch in the line y equals x. That'll sort of give me a point of reference and help me as I sketch this. But I need to take every ordered pair and reverse the x and the y. So when x is 4, y will be -2. So I'm going to come over here to 1, 2, 3, 4, come down to -2. And that point will be on my graph. When x is 2, y will be -1. So I go to +2, -1, I put that point on. When x is 1, y is 0. So that's going to have this point right here on the graph. When x is 1/2, y will be 1. So that's going to be up here somewhere. And when x is 1/4, y will be 2. So probably up here somewhere. Now, carefully, as you sketch this in, here's what you will see. This is going to come this direction. This is going to come up and be an asymptote getting closer and closer to the y-axis. Now, I realize because of my stylus this isn't very exact, but hopefully you can see this point of intersection, although it may not look like it's dead on y equals x, that's just my error in graphing, it would intersect somewhere on the line y equals x. And I should be able to see that these two asymptotes, where we're getting close to the x-axis here and close to the y-axis here, if I fold on the line y equals x, they're going to match up. And these curves that are going through the fourth quadrant and through the second quadrant, again, if I fold on the line y equals x, they're going to match up. So that is the graph of the inverse. This one is the exponential function. This one is the inverse, which is the logarithmic function. Now, to get domain and range, again, we switch those domains and range from the original, and that means our domain would be 0 to positive infinity, and our range is -infinity to positive infinity. We have one more page of notes, and we'll be done. Now, this simply explains that we can still have fractions for bases in logarithms. And again, if we remember that the original function here is y is equal to the log of 1/3, base 1/3 of x, if I were to switch the x and the y, okay, what that's asking me is what would be the way this is written, a logarithm is simply saying I'm looking for the exponent that 1/3 would be raised to give me x. So if I switch the x and the y, that means I'm going to have to take that base 1/3 and I will raise it to the x power. Okay, we'll look more at how to get these inverses written, but that's all that we're going to do. When we go to exponential form, the base does not change. All that happens is that we switch the x and the y. So we could fill in the table here on the right, and we will end up having a graph that will be very similar to what we saw on the other graph. I won't take time to go through and plot the points, but you are welcome to do that if you want to practice. I will tell you that on the computer, obviously you're not really plotting the points, you just have to recognize these. So if you're able to recognize these, you will probably be okay. If you're in my face-to-face class, at most, I would ask you to graph an exponential I would not ask you to graph a logarithmic equation. We'll pick up with more when we get to section 4.2.